Okay, I think we're live. We've got a few people coming in.
Screen.
Just letting everyone know that we are recording this, but your microphones are all muted, so it's okay. Let's give another minute and we will get underway.
Chat box out.
And while we're getting started, Amy's going to put a poll up. Which will just ask where you're listening from today. Oh, yep, just checking the chat. Oh, no, it should come up on your screen. Everyone's in the office today. No one on the tractor today, Dale.
That is indicative, I think.
Yep. Okay, I think we might get underway. So good afternoon, everyone. Welcome to the second Friday Climate Forum, which is part of a new webinar series that we're delivering over the next couple of years through the Eyre Peninsula Sustainable Ag Program, which is funded by the EP Landscape Board and the Australian Government's National Heritage Trust. Today's session is focused on interpreting climate forecasts, what they can and can't tell you. So this will be more of an ongoing resource rather than a situation on what the climate is doing at the moment. We're very pleased to be joined by Dale Gray, a seasonal risk agronomist with Agriculture Victoria. He'll talk us through the different climate models, how they work, interpreting climate predictions and model accuracy. And just before we begin, a few quick housekeeping notes. Just keep your microphones muted unless invited to speak. And you can submit questions through the Q&A or the chat functions during the session. We will run through without questions, but we will hold questions for the end. I'll be piping up to give Dale some timing warnings so we stay on track. And thanks very much for joining us. And I'll now hand over to Dale. Take it away, Dale. Thanks very much.
Rightio. Good afternoon to the good people of the Eyre Peninsula. Greetings from Bendigo, where it's an absolute bluebird here today, and we had a very light frost. I'm going to talk about today. I'm going to start off. Unfortunately, I'm going to be talking about maths and physics, but not in a detailed sense. We're just going to talk about briefly what models are and how they work. They're a bit of a black box for most people, I suppose. You put things in and you hope things come out. The models that we're talking about today are the seasonal climate models that are run usually on a daily time step and go out 6 months. And these are run on very large computers. They take a lot of grunt to work. And we're talking about a coupled model here, which has models of both the ocean, both at the surface and at the depth, and the land in terms of its topography and its ground cover and moisture, perhaps soil moisture as well, and the atmosphere above, the air from ground level upwards, up to very high in the atmosphere. And it's all done on a grid. So this is sort of the best demonstration of a model I could find, where you've got the world is divided up into squares, and each of those squares is really a layer of both a surface with some height to it as well. So you can see a thinner block of data there, and then they get sort of bigger as they get further out from the land surface. And so this is kind of what we have. This is a little representation of that sitting over the UK, because this is a UK Met Office diagram where sitting over London, you've got mathematics occurring in squares upwards, and out in the ocean off the French coast here, you've got the ocean in different depths going down as well. And all these boxes represent, I say all in inverted commas, is mathematical physics. Things that are obeying the laws of the world that have, a lot of those were discovered in the 1800s. Things where you've got the exchanges of direction, where movement is moving, wind and things like that. Heat, is heat getting greater or less? Are things losing heat or gaining heat? And is moisture, what's happening to there? And there's, there's pressure there as well. Pressure, volume. These are all physics things. If I did physics and never really liked it, but there's people who absolutely love this stuff, and it's their attempt and aim is to make mathematics make a representation of the way the world works as closely as possible. And so these boxes are called resolution, as we'll look in soon, and the size of the box is different for the model. This is quite a coarse model here. You can see that, from southern to northern Australia here, there's 4 boxes. And so the mathematics going on is only the maths is integrated in that whole box and the layer kind of above it. So everything's predicted in blocks at the horizontal and the vertical, and those blocks are talking to each other to their north and to their south and their east and their west, and to underneath if they're in the ocean, or soil, into the soil moisture if they're over the land, and up into the atmosphere above. And everything's sort of talking from one box to the next one. That's talk in inverted commas as well in terms of the mathematics. So the first thing I want to talk about today is resolution of models. This is quite an old graphic now. And the critical thing is, don't see more accuracy into models than the resolution allows. And the resolution is how many squares of mathematics in the answers that the maths spits out are appearing on a map that you might be looking at in terms when you're looking at a climate forecast. So for instance, here we've got the old computer model we used to run at the WE, that's the Royal We, I've never done it. The BOM used to run, called POAMA, which we developed in Australia. We used that for 5 years between 2013 and 2018. And these were the outputs in terms of the squares. This is very coarse resolution. Every one of these squares is 250 kilometres square. And there were 17 vertical levels going up. And then the resolution in the ocean was a bit better. And there were 25 levels going down in the ocean of this model. But you can see for the Eyre Peninsula, well, there's 4 squares at best that represent the whole Eyre Peninsula there. Then in 2018 until now, we've moved to the Access model, where the resolution improved dramatically to 60 kilometres by 60 kilometre squares. That's way more than the average farm, even in Northern Australia. And the ocean is now 25 by 25 kilometres. We've got 85 vertical levels going up, 75 levels going down in the ocean. And now we've got topography and soil moisture to 6 metres as well. Why resolution is kind of important is because the Great Dividing Range down the coast, so things like topography, the Hamersley Ranges, the western tiers of Tasmania, not able to be actually physically modelled in a model that's 250 by 250 Ks, because those phenomena are smaller than that. But this data, these models, these graphics are for the same timestamp, and you can see just the effect of resolution instantly makes things look a bit different and a little bit more believable. You start to see an effect of the Great Dividing Range up the coastline here, for instance, of New South Wales. And these little brown bits here are sort of a bit bigger. And so resolution is useful. But just remember, though, even at the moment, 60 by 60 Ks, if someone's promising you to give you a forecast for your property, and you can punch in a location into most models in the world, particularly just a weather model, and it's coming up with a forecast, just remember that the maths has been done on quite large areas than just your farm, and it's going to be pulling the closest bit of square to your farm or your town for that answer. And that might be, you might be right in the middle of the square, or it might be coming from 30 k's away in terms of the model answer. So the first thing I want to talk about is we're going to talk about the different ways that computer models present their climate forecasts. And we're comparing apples to apples. We're looking at the June to August forecasts from a range of different models from around the world here. This happens to be Access, the Australia's Bureau's model. And the first way we're looking at here is an anomaly from average. So you run the model physically is raining in its model, it collects up the rain, and then it maps, is the rain less or more than the average? And so where we've got white appearing on this map here, this model is predicting that the rainfall's in the realms of normality. And if it's blue, it's wetter than normal. And if it's brown, it's less than normal. So you can see here for the Northern Eyre Peninsula, or the Northern Eyre PP, it's predicted to be 10 to 25 mils drier for the next 3 months. And you'd go, well, that doesn't seem much drier at all. And then you've got 25 to 50 mils less down here on the southern part of the EP. And what I find with these are called deterministic models. These are saying how wet or dry it's going to be. And when I first started out in this game 17 years ago, these were the most attractive to me, rather than the probabilistic ones we'll see soon. But I soon became to learn that these aren't as good as they seem, because it's tempting to look at these forecasts of absolute less or more rainfall prediction and use them at face value. But for reasons different for every model, some models are just wetter, some are drier. There are biases in the model, and that bias can often try to be corrected. But the absolutes are not usually helpful here when I've been looking at these things every month for the last 17 years. It's very much about going with the vibe. And we're going to hear that a couple of times today. And you can see the different colours here that, north of Papua New Guinea and the Solomons is predicted to be much drier up here. Out at Tuvalu, it's predicted to be very, very much wetter. But over the EP, there is a drift towards drier from that model. And so that's the kind of vibe we're getting. I've seen predictions of a little bit drier just turn out to be it didn't rain at all, hardly. And you don't often down in this area of the world get models really drifting into this extreme. You tend to see that much more in the tropics. Here's an example. Thank you. Here's an example of a whole heap of other different anomaly forecasts from different agencies: the UK Met Office, the American Bureau, the German Bureau, a collection of North American models, NASA. And you just look at the scale generally. They're normally talking something about millimetres per day or millimetres for the whole 3-month period that you're looking at. And you're looking at these models and getting a feel for, are they going into the drier side or into the wetter? What's interesting, in all of these models, bar the German one, all of these models are kind of sitting on the fence. And they're for the same time stamp that we're going to look at soon when we look at the probabilistic models. There's no real signals for drier except that German one that I showed there. I mean, they could be putting 12 of these up or more, but just gave a selection. They have different ways of showing it, but it's really just a scale of normal and how much rain, drier or wetter. Which brings us to the most common type of way in Australia that we see climate forecasts, which I call a binomial forecast. And What's interesting is that people may not know this is the Bureau's access model run from a couple of days, yesterday in fact. And the map that we see here is made from the last 3 days of model runs, where they run the model 33 times a day, and 99 model runs are included in this answer. It's not like a weather model where you run it once and it says it's going to be 10 mil at Woodner or 50 or 2. We get 99 possible plausible outcomes every time we're looking at the data from this model. And this is the binomial forecast, where we're looking at the chance of exceeding the median or average. And by definition, if you looked at all the data in a record, 50% of the time it's above median and 50% of the time it's below. So when you're sitting here on the white, it's tempting to think that that means a forecast for average, when in fact, so out here, in fact, that means there's an equal chance of exceeding average and an equal chance of being below the average. So when we look at down near Cummins, currently it's 1, 2, 3 colours of brown shades. 1, 2, 3, we're between the 30 to 35% chance of exceeding the median. And in your head, you need to then flip that, subtract 100 from these numbers, or this from 100, and it's telling you that there's a 65 to 70% chance of not exceeding the median. Both of those things are equally plausible. So this forecast, you don't look at this forecast and look at Kangaroo Island and go, gee, it's not going to rain. It's saying there's a low probability of being wetter than the average, but it's saying there's a high probability of it being below the average or the median. The model will never be wrong. The answer is somewhere between these two, and it's all about the probability. The odds are going drier. And here's there's less examples of the way this is done in the world, but here is the UK Met Office provides that answer, and you can see it's a little bit drier there. This is the USQ, Southern Queensland. This is the forecast just based on the Southern Oscillation Index. And this is a USQ model, which looks at the most accurate model in the world and then puts its forecast in the boxes. And all three, these are just all the chance of being wetter or higher than the average or the median. This is tercile. So we've gone to a choice of above and below the average. Absolutely no information about the chance of actual average. And so the next thing we go to is what's called a tercile. Tercile is just a fancy term for 3. And the historic chance of being either in the bottom tercile or the middle tercile or the wetter tercile is 33.3333 repeating percent. So you always got to think, when you're looking at a tercile forecast, we're thinking 33s as the base. And everywhere you've got white on this map, 33% chance of this is the anything could happen forecast, what we'd often call neutral, which is not average. Anything could actually happen anywhere it's been white. And remembering, this is once again a result of 99 model runs. And so if we look once again in the middle of the Eyre Peninsula here, we've got 2 colours of brown. We're 50 to 60% chance of being in the lowest tercile of rainfall. So not looking at the one in the past, which was being a 65 to 70% chance of not exceeding average, but who knows by how much. Now we're able to say that this is predicting a 50 to 60% chance of being in rainfall in the bottom third of the record. But by definition, that also means a 40 to 50% chance of actually being average or wetter if you're the glass half full person. So there's almost a doubling of the odds there. There's certainly anywhere you've got this 60 to 70% colour, which is nearly all to the south of you in the Bight, 60 to 70% chance of being in the bottom third of the record is a doubling of the odds of normal of being drier. And so this is without a doubt the most common forecast that's done in the world. This is a large ensemble of models from around the world. This is the UK Met Office. This is Japan. This is China. This is the European Centre. And now you can see that all of them are now talking about percentage. It's about chance. And it's the chance of being either below normal, average or normal, or above normal. They have different ways of doing this, but some of them kind of keep the normal bit grey. Some people, most of them put this sort of, some people call normal neutral, which is confusing as well. But normally white means 33% chance of anything happening. And the UK Met Office gives you sort of three maps to chance, because when you put this in one, all you're looking at is which one of these three likelihoods is the most likely and mapping that. This forecast from the UK actually says, well, what's the chance of all the other ones as well? So you can, sometimes you get weird forecasts where the chance of wetter is high and the chance of drier is high and the chance of average is low. Not very common, but occasionally you do that, which these forecast types don't kind of allow. The other thing I'd point out here is that these two maps here, you can see are very grainy. And so they're showing the individual results for the resolution of the model. So you can see that this is coarser than the Access model, but it's definitely better than the POAMA one in terms of its resolution. And this one is probably a similar resolution, this Japanese one. But these are real model outputs. These ones here have all been massaged. They've all been smoothed, statistically smoothed to make nice fine boundaries. And that's another take-home message for today, is that models do not work in smooth boundaries. They work in squares. Humans seemingly don't like that, and they try to make things smooth to make them look nicer. And so you get a lot of the world's model outputs, including the Bureau's one, coming out in a smooth line arrangement. But just always remember that the individual maths behind that is not smooth. It's granular and square.
20 minutes now.
Thank you. Many of you may or may not know that by clicking anywhere on the Bureau's map, or by typing a location in, you can get a different forecast. And I just typed in Lock, and it's given us what we see now, what's fancy term is a quintile forecast. It's actually in fifths. Quin is 5. And the 99 model runs have all been binned into the probabilities of being really wet at decile 9 and 10, wetter at decile 7 and 8, average at decile 5 and 6, a bit drier at decile 3 and 4, much drier at decile 1 and 2. And now we're getting even more information here, a spread of the really wet and the really dry, and maybe even the average. Once again, the model will not be wrong. What happens in the next 3 months is somewhere in here. But we can see just from this forecast, which has been saying it's drifting drier, has cut the odds of it being really wet in half, and it's increased the odds of it being drier by about 50%. But the chances of it being normal haven't changed much at all. So this is not what I'd call a very strongly skewed model towards the dry, or wet for that matter. In this one here, we've got only a 14% chance of much wetter rainfall for the next 3 months, a 19% chance of average, and a 37% chance of decile 1 to 2. So it's a swing in the odds, but it's not a dramatic forecast where you might look at the brownness on that map and go, oh, gee, that looks terrible. So what we've just shown is 3 separate ways of looking at plus or minus 50%, where it is in thirds to where it is in fifths, just from the Bureau's model. Now, as far as I'm aware, the Bureau of Australia is the only model that gives you this depth of information. Most other people are sticking at that tercile one. And this has been, you know, in my opinion, a vast improvement on our plus or minus median forecast that we've had for a long time. I do want to just go now about, I'm going to sort of start looking now at skill. And in particular, how many minutes have I got now, Naomi? Not much.
9 minutes.
9. Oh, cool. What we're looking at here is just a whole suite of different climate drivers. Some of them you might have heard of, ENSO, El Nino, La Nina, the IOD, Southern Annular Mode, things spinning around Antarctica, the Madden-Julian Oscillation, a cloud wave in the tropics, and the subtropical ridge of pressure in terms of its position north and south of normal or its strength. And I've looked at a heap of scientific papers and put a tick in the box when the rainfall on the Eyre Peninsula has statistically been affected outside just regular variation in terms of being wetter or dry, and put a tick in the box. And so a few things pop out of that, and not the first is really the fact that January, February, March and April, the start of the year, there's just a complete absence of ticks in the box, and December is not much better, and November in your area is not great either. And so the business, when climate drivers actually affect rainfall, is in this May to October period, the critical time of the growing season. But in terms of pre-planning, this time of the year is the worst. You might have heard or not that we have a thing called the autumn predictability barrier. This occurs because models find it very hard to predict what's going to happen for winter and spring and autumn, because none of these climate drivers are doing anything that's greatly affecting the climate at that time. And it's only when the climate models are able to predict something like these things going on that they then have something to go outside of normal and go, oh, I think it's going to be going wetter or drier. So the growing season is where it is at for us in Southern Australia and for croppers, which means decisions that are made in autumn are best made in the absence of climate forecasts, because the skill, by the time we put the crop in the ground, model skill, as we'll see, is usually pretty poor. And so now what we're going to go is just look at actual historic accuracy of models. And we're looking here at the BOMS Access model, where I think they've done their historic reenactment here from 1981 to 2018. They've set the world up in all of those months and years, and they've let the model go and seen what it spat out and compared that to actual. And so anywhere you're less than 50% on this chart here, if it's green, it's good. And the accuracy of this model is not that bad. It's probably better than people think. But you can just see that in summer and autumn's actually seemingly not that bad, but winter it surprisingly drops away a bit for the EP, and then spring it comes back better. I'm not sure if that's an anomaly or not, or whether I believe it, because if we look at a whole suite of other models, that is often not the case. You can certainly see for Eastern Australia, Southeastern Australia, spring is kind of the purple patch for this model. This is a different model. This is the ECMWF model. They have different ways of presenting skill in terms of the statistics. We're not going to worry you about that. Let's just look at colours. If it's orange, it's better accuracy. If it's blue, it's worse. If it's grey, there's none. Summer, autumn, a bit. Winter, a bit, but nothing to the north of you. And spring, well, there's a lot more colour going on there, but there's none of the orange colour. That model pretty much sticks it. It's better than flipping coins, but not a lot better. This is the UK Met Office, different way. Remember, they have the chances of being wetter, average or drier, and they test the skill on that differently. This is once again for summer, autumn, winter, spring. If we go for the chances of wetter, there is once again, better than 50% is better. We've got some skill through here for the wetter sweet, but you can see that there's more, the colour gets denser as we get to spring. And when we're drier, that kind of essentially goes on as well. But the probability for predicting average, interestingly enough, in a lot of models is often poor. They're often much better at going for more dramatic deviations away from average. This is the American Bureau. They keep things very simple. Where the model has no skill, they just block the map out and don't tell you what the forecast is. There's a little bit of white or coloration we can see in summer, autumn a little bit as well. Winter is no good, and spring we're back in business. This is the Japan Met Agency. Summer, once again, blue is better here, a little bit in summer, autumn a bit split. Winter gets bluer, spring much bluer. So the real take-home message is there is that model accuracy is not great in autumn or summer. Winter, spring is where it is better, but individual models have a bit of variation about that. I thought I just might touch on how do we improve accuracy in models. This is something that progressively goes on every day in the world and every year and over decades. And there's three ways that basically happens is better physics or maths of the way the world works. There's people who are living every day trying to improve that, and bless their souls. Better initialization of the model. You need the way the world looks right now to be as close to the way the world looks. And we probably haven't had as good a ways of doing that as now. That keeps improving with satellite technology and all the buoys and things getting data in the ocean to set the world up. And then there's the issue of just grunt, better resolution. So as you get mathematics in smaller squares, if we looked at that very first example I gave, just going from 250 by 250 to 60 by 60 means your computer had to be 16 times bigger to just do the surface, and it had to be 5 times bigger to do the up above and the below. And if you multiplied that out, I think 80 times. There's 80 times more square cubes in the new Access model compared to the old Poema one. You need a bigger computer. And computers do keep getting bigger. This is the Bureau's computer here. That's the one they used to have. This is the one they've got at the moment. Massive thing hiding somewhere where no one knows. Beavering away many times a day on punching these models out.
1 minute, Doug.
Thank you. I think this is close to my last one. So the thing is here is not to be trying to pick winners. What's important is to look at a suite of different models, because sometimes some models do something very differently. And so these are the predictions for May for the Eyre Peninsula. They're all predicting an El Nino. The Indian Ocean prediction is all over the shop. And if we look at rainfall, we can see, bless their souls, that the Chinese model is going for wetter for the Eyre Peninsula. And if that was your favourite model and you were looking at that, you'd be going whoopee-doo. But you'd be crazy to be looking at that in the presence of all these other models who are predicting that there's more likely to be a drier outlook. And this doesn't mean just because there is a consensus it will be drier, but you just need to know what is the spread? What is the spread? Is it all over the shop? Is it all leaning one way, or is it divergent? Is it actually all over the shop? At the moment, that forecast is definitely predicting rainfall more likely in the driest third of the record. So models have skill, but at certain times of the year, none in some, and the time and location matters in terms of the year and where you're situated in Australia. Looking at a number of models is always better than looking at one. And a bit like the castle, you've got to think Dennis Denuto, it is about the vibe. This is Dennis Denuto here, the lawyer. It's about the vibe. It's about what are things pointing towards, rather than trying to look for absolutes. How dry is it going to be? Because in my experience of looking at that over 17 years, how dry has never been, or how wet for that matter, has often come from models that have only drifted a bit wetter or a bit drier. So I'm going to leave that there, Naomi, and we'll take any questions if there are any.
Well done. That was spot on, Dale. Yes, we do have time for questions. So if anyone's got any questions, please pop them in the chat. Make them as curly as you like.
You can see Peter Heyman was there. He was probably capable of giving this talk perfectly well himself.
He can probably tell us what you missed out, Dale.
Oh, yeah, there we are. There's probably a great deal. There's 2 slides I missed there, which was probably some slightly extra context of how to use this. But if I've got extra time, I might go into them. If there's no questions.
I will just chat away for a minute on what I took out of it. But
yeah, right, yeah, go for it. Yeah.
My key takeaways are model accuracy is greatest in winter and spring. So maybe don't put too much emphasis on anything outside of that. Smoothing versus boxes. Mathematical boxes are much better than smoothing.
They're more accurate.
More accurate. And it's the vibe, which I think is definitely a takeaway from today. So.
Yes, I think there's people trying to pretend that these models are, good enough to run the farm on. Whatever the answer is, well, that's what we act on. And the reality is that is not the case. There's always so many other things going on that we make our decisions on. And Peter and the RiskWise team do a fantastic job of elucidating that bit better than I often do. I've got a bit of a hierarchy here that I often use about what increases the confidence in a model's output. The first is that the models are all singing from the same hymn sheet or not. It's the time of the year where there is skill. Is it winter or spring? You can see whether the ocean or the atmosphere is set up in a way that could cause the model to be going wetter or dry, like it's not pulling its prediction out of its fair old derriere. It's actually, there's a reason for it. You can see that the ocean or the atmosphere is actually moving. It's actually moving in the way that the model is forecasting. And then finally, that you actually have the climate driver it's predicting actually formed and coupled between the ocean and the atmosphere, means that there's a much higher chance that the outcome is likely to happen. And the final is that the models actually have good form at predicting what is going on, and they've been doing that in the previous months. If the models have been predicting drier and it has been drier and they're still predicting it to be drier, it was pretty hard to go against both form and consensus. And then and in autumn, when there's not much information, you just really got to place your emphasis on the known knowns, things that could deviate you from an average outcome for your farm. And without a doubt, the most important one of those is soil moisture. But it could be how last year's financial return went. Could be world pricing, perhaps. Could be weed profiles in paddocks. But these are the things that you use to make your decisions in autumn, rather than expending a heap of effort on a forecast, which is, often at 50-50 flip of the coin at best. No more questions, Naomi?
Nothing has popped up. You must have explained it perfectly, Dale.
Or not, yeah.
But I will let everyone note that there is a link to a short evaluation form. If participants want to click on the link in the chat that Amy's popped up for us, it'd be great if we could get your feedback. And I have a comment from Peter Heyman, Copernicus.
Yes.
For a question.
That's right. I think I know what he means there. There's so there's a lot of individual models that you can look at in the world, but there are some ones that we call ensembles where they've already put a whole heap of models together, and that's the royal we, Models which include a lot of other models are often more accurate than individual models by themselves. And we see that in weather and engineering and all sorts of things. So the Copernicus model looks at, I think, 7 or 8 world computer models and puts them together and gives you, and you can look at the individual ones, and then you can look at the blend of those as well. But then there's also an Asian Pacific community one based in Korea, which looks at a suite of models. And then there's a North American ensemble, which looks at 10 North American models and looks at those combined all together. So we can go back to some of those. So these are the ones, these are individual models here. These are ensembles. This CS3 one here is the Copernicus one that Peter's talking about. This is a couple of others as well. But so whenever you see an ensemble model going for something outside of normal and neutral, well, there's more than just one model doing that, Naomi. There's more of them. The majority of them are going in a particular direction. And so just by looking at, an ensemble, I suppose, often gives you a very quick look at what's going on compared to looking at, 8 separate ones. And that's, essentially that's what I'm doing here in that suite of 8 models there. You can make your own ensemble up in your own head by looking at them. But then there's actual ensembles of collections of models themselves here, of which the Copernicus is one of them. And I'm hoping that that's what Peter was alluding to.
Maybe he might comment. First time I'm probably hoping that the Chinese model is the most correct.
Yeah. It's sticking out there, I've got to say. I looked at that this morning. I've got a feeling they're running that model. So the Bureau's model is run, this is Access, it's run like every 4 or 5 days. The American model is also run every 4 or 5 days. I've got a feeling the Chinese model is that too, because it wasn't saying that when I looked at that the last time. That looks like that's changed a bit. But I mean, what's interesting is it's got a little wetter section coming into the Eyre Peninsula, and only the Eyre Peninsula up to the north west of you, on a backdrop of everywhere to the east of you being drier. So sometimes it's interesting to look at the spatial bit as well and go, well, do I believe that the Eyre Peninsula can be wetter when everywhere around it is drier? That to me seems a bit less believable. That model has jagged a couple of wetter events, it seems, to get that outcome to happen. But we in 3 months' time, Naomi, we'll know, and
we will.
We can verify. We can verify and go, well, who got it right?
Excellent. Thanks, Dale. And a reminder from Amy just to fill in the evaluation if you haven't had a chance to do so yet. Thanks, everyone, very much for joining us today as our second session for our Friday Climate Forum, delivered through the Sustainable Agriculture Program on Eyre Peninsula. So we really do welcome your questions and ideas for future topics. If you have got anything in particular you would want to hear about, we can certainly build that into the program. We make this up as we go, don't we, Dale? So
well, we're coming back in a fortnight and we don't know what the topic is yet, Naomi. No.
Okay, so there you go, open slather. But thank you very much, Dale, as per usual, for all your prep that's gone into this. Thanks, everyone, for attending, and we look forward to seeing you at the next one on the 12th of June. We're scheduled in for, so thank you all very much. Have a good day.
Catch you later.